Hello everyone. In this video, I'm going to continue going over the general concepts that's on the Calc 2 Exam 2. This applies for both MA 162 and MA 166. So in the last video, I went over points 1 through 4. So in this video, I'm going to continue on explaining partial fractions, improper integrals, and some of the intros to sequences and series. Continue on to partial fractions. So partial fractions is for when you have a integral of denominators that can be factored into simpler just like something over like a lower power x. So for example, you see the example in the middle here. We have a square, x squared and x and a constant in the denominator. There's not really a lot of identity or integral that can really easily deal with that. But if we are able to factor that into the right hand side, we have like an x plus something or x plus something in the first power, then this can use it will just be, you can use u sub and it will be just ln x of something, right? So then the main idea then is that the ln the integral of 1 of x is ln x, right? And then you can u sub for like if you have like a x plus 6, right? You can u sub for x plus 6 and it will be just ln x plus 6, right? And then if you have a constant on top, right, it's 6, then it's 6 ln x for the final integral. So this is right, and just as another reminder, right, these partial fractions tricks up, these apply where you can't use any other things, right? If you can't use u sub, you can't use by parts or any of other ones, then try partial fractions, and it comes in it comes in when you have a denominator that can be factored. Right. So for example, then we have on the bottom x squared minus 7x plus 10, right? For that, it's actually factorable but with minus 2 minus 5, right? Then we can say that we can set it up as a since we don't know the top part, we don't know the a and b, the constants that is going to go on the individual factored fractions. So we're just going to have two variables, right? We can have, since this is two parts, we have two variables a and b, right? And then we can solve for that a and b, as in and with two different methods. So the two different methods for solving a partial fraction expansion is what we call it. Is A, solve a system of equation, which I will go over in short, but B, or number two, is Heaviside method, or you can search up cover up for partial fractions. It's a pretty handy way of solving partial fractions without getting into systems of equations, but Purdue Calc 2 does not teach it. Also, it's a different way. It's a similar way, but it starts at a different point. So it's a little confusing to me. I use this system of equation all the time, but I have used Heaviside before. If you're interested, though, it's you should be able to search up on YouTube. There should be great videos explaining it, and it's pretty convenient too if you get it. That of course, but what I mean by solve system of equations. So we have a over x minus 2 and b over x minus 5. Right? Why did I set it up? So what I'm saying is that I'm just making the fraction on the left equal to something that's simpler, that is two different fractions adding on to each other. Right, this is just the left-hand side, but factored. I'm saying that there's a certain fraction plus another fraction that this equals to, right? So in this case, right, how do I solve for this a and b? You might say that this equation has three different variables and you only have one. So the clever part is that once you combine these two, combine that 2 on the left-hand side, right-hand side, then you get something like this. Right? Over here, I switch the left and right. So I have a times the other. So I have a times the other part, the other denominator to get to the common denominator, right? And then we'll have b times the x minus 2 part. So now I made the left and right sides denominators equal, so I can now cancel it out by multiplying by that denominator on both sides. So then, I should erase these for now. That's a 5. Oh my. So now I have an equation like this, whereas it's just I expanded it to, so ax minus 5a, etc., etc. So now the clever part is that you can take the different powers of the x and make it equal to each other. So we can see that right, no matter what a and b is, right, it doesn't really equal to x, because x in this case is what we're varying, as in the dx, right? It's varying over, if you think about like a graph, right? You take the area under the graph, it's the x is varying over a range. So that's not really like a constant that we're looking for. We're solving for a and b, which are the constants that we don't know. X is a variable that we are varying. So in that case, right, this 5a here and this 2b here can never equal to the x part. So therefore, we can write out the second equation here, which is negative 5a minus 2b equal to negative 7. Right, that's the constant part, the parts of this equation that does not contain x. Now, similarly, we can write out this first equation with all the x containing parts. Oh, I forgot a 2 here. So this part, right? Similarly, the negative 5a and the negative 2b can never equal to like a 2x or anything containing an x, because it doesn't have the variable x that constitute like a range of numbers over in a graph, where you can think about it that way. So in this case, right, we can have just two equations, and then we can divide x from both sides on the equation 1 to get what we have over here, which is a plus b equal to 2. And in that case, now we have a system equation of two equations, right? Equation 1 and 2, and two variables a and b. Right, this is pretty simple to solve. A is 1 and b is 1. So now I can go back to the original equation I have up here with the integral, right? And I can replace this original complex fraction I have with a and b in factored form. So now it equals to integral of 1 over x minus 2 plus 1 over x minus 5, right? And that is pretty easy integral. Just take ln of x minus 2 and ln of x minus 5, right? Right, I will advise right, when you have just like a x, that's fine. You can just take ln of that. But if it's like 2x minus 2, right, you might need to do the actual u sub. Because if you make u equal to the 2 x minus 2, then du is actually 2 dx. Right, and there's a 2 that need the chain rule. So that is something you can worry about the chain rule part of doing the final part, right? You don't want to miss a point because you forgot a chain rule and you did all the hard work for the for the partial fraction expansion. Right, and then the big note here is that the numerator should have a lower power of or order than the denominator. For example, here we notice that the numerator, the highest power numerator is a cube, or x to the third, and the highest power of the denominator is x to the second, right? So in this case, we can tell that we can actually factor, or rather use long division to make this simpler. What I mean by that is I will go over here and do long division. So long division, the goal is just to get the numerator to be a lower power, and then you can also factor out some of the complex numerator powers. So it's easier to do partial fractions. Right, the example here, I have a different example, but the example here, I have still a cube on top and a square in the denominator. So doing this, just like how you learn division when you're third grader, fourth grader, right? We have the divisor, or I think that's what it's called. The denominator on the left hand side, and then the numerator that you're dividing on inside the division, right? And then I say, what is the highest power that I need to fit into like a x to the third, right? For the highest power here, right? I don't need to worry about the x, or I don't need to worry about the x or the other numbers. I'm just worried about the highest power of the divisor and the highest power of the numerator. So in this case, right, it will be 4x, right? 4x. For 4x, right, we'll have 4x times 2x squared. That will give us ax cubed, right? And then I will do the rest, right? Plus x, then I have plus 4x squared. This comes out pretty nicely. Same thing with division, right? You minus this one by this one, right? So it's 0, 0, and then we have a remainder of 3. So this expansion would be equal to 4x outside plus 3 over 2x squared plus x. All right, that's the gist of long division. And this applies, we have a higher numerator power than denominator. But I will move on to different cases that you might encounter with partial fractions. So for example, we have here, I'm not gonna write out the integral of each part because that's really not the important part of partial fractions. Partial fractions is about expanding complex fractions, right? So here we have 2 over 5x cubed minus 4x squared. Notice how for both of these contains a x squared, right? And this x squared can be factored out over here. So it's x squared times 5x minus 4, right? But notice the x squared here actually has a what do you call it, a repeated linear factor, right? It's x times x, right? This applies where you have if you have x plus 1 squared, right? It's x plus 1 times x plus 1. It's a repeated factor like you can write it out and you see that it's repeated with like a higher power. In that case, the expansion you should have is it needs the first linear term, so where you have x, a over x, and plus b over x squared. Notice the sort of formula we have here, since this covers all the bases of the getting back to the common denominator later on. But if you have a repeated linear factor, you need to write out the first linear factor term, and then the square of that, and then all the way up to however many times that repeated linear factor is, right? If you have x cubed over here, then you have a over x plus b over x squared plus c over x cubed, and then plus d over whatever. Right, and then here, in case 2, so what I changed here is that instead of the minus 4x squared, I have minus 4x. So in this case, the x can be factored out, right? It's just an x, but then the remainder of that part is 5x squared minus 4. The problem with this is that 5x squared, when you do common denominator like combination, it's sometimes when you only have like a b, let's say you have a b over 5x squared, that will actually not cover all the bases because this x squared is skipping the x term, as in if you combine it, it will not combine it with like the x over here, then you wouldn't have the highest power of your solution. Therefore, what we do is instead of writing just b, we have bx to cover that extra base that we haven't covered with x squared. Then we say plus c for the constant part. All right. So in this case, we have a over x for the x term, and then bx plus c over for the x squared term. And then here's a little expansion that I would do, right, when you get back to the common denominator. So you can get a highest term of like one less. How I explain it is one less than the original denominator. So notice here I have bx squared, which is one less than the common denominator that I'm going for, which is x cubed. And this kind of has to do with uh, the long division part I was talking about, where the numerator has to be lower order, at least one, than the denominator. And this is what we are getting to, so that it covers as one. Make sure your numerator, after you combine it, it covers all the powers up to one less than the original denominator. But if you like follow just like bx plus c model, right? If you have like a 5x cubed minus 4, something like that, then you would need like bx squared plus cx plus d, right? You just add more terms to be able to cover all the powers. So here is example. Right, for this, we have 1 over x minus 1 squared times x minus 2 times x squared plus 5 cubed. And this covers a lot of bases. So this covers the repeated linear term. Right, these two are repeated linear terms, or rather, that's not linear, but And then this is case 2 where you have like a higher power that cannot be reduced. Right. So let's get to it. We have, first of all, the repeated linear term, x minus 1, and then x minus 1 squared, right? Then I'll use a and b, and then c for x minus 2, that's just one linear term, and then I have then 3 terms for repeating x squared plus 5 3 times, and each time I have a constant plus a x term, right? dx plus e, fx plus g, right? These are all needed because of the higher power of x squared that cannot be reduced. And you shouldn't be too scared about this since it's like a huge fraction that you just expanded. But usually when this happens in an exam, they would just stop here, right? They would just say, what is the correct expansion, right? They might have like not these. They might just say, oh, is this correct? Right? And it's not the because you're missing the x terms on these, right? So those are those should be pretty simple once you get the gist of it. But it shouldn't be too hard if you see like a super big expansion like this. But the other tip I will give you is this on the bottom. Right, the integral of 1 over x squared plus 1 is tangent negative 1 of x. This is identity, an integral identity that you should know from calc 1 probably, but it will come in pretty handy because sometimes you have like expansion that might be like a of like x plus 1 plus like b for x plus 1 squared, repeated linear term, and then plus c over like x squared plus 1. Alright, this actually cannot be, you can't really use sub or do stuff like that, right? So it's helpful to remember this tangent negative 1 integral because a lot of proc questions actually have this. And you can just say, well, I recognize that, and you can just write the integral straight out. Now let's move on to improper integrals. And improper integrals is defined when there is a infinity anywhere within this integral. Sometimes it might not be the limits of the integral. In our example 1, it is in the upper limit. There's an infinity, but it might not be. For example, for number 2, we have limits from -1 to 1, and that range is defined. But if you can see the shape of this function, it the middle part approaching 0 for both sides are approaching infinity, and that's something that you might need to use improper integrals for. So let's move on to how to solve these improper integrals. So for example, I have limits from 1 to infinity of 1 over x squared. All right, this should look something like this. It's the same thing as the 1 over x, where it has like the curve over here, but that is just flipped up because there's a square, right? And then I'm really concerned with just this part. And then, so the way to solve these is take the limit of like a extra variable. In this case, I use b, right? I take the limit of b to infinity and I replace that infinities in the integral with b. So now it's a variable rather than the infinity. So now I can take the integral of 1 over x squared, and that is just negative 1 over x. Right, that's just simple chain rule. And then, right, the limits, we're going to take this from 1 to b approaching infinity. And now we just plug it in, where it's negative 1 over b and plus 1. And then it's just putting b back in, right? Putting the infinity back in, and that would be 0 plus 1. So this improper integral actually has a value to it, right? When it has a defined value, we call this converge. This convergent. This improper integral is convergent, or it converges, right? And in other cases, it might be the value come out might be like infinity or some wonky stuff. Usually it's infinity, where it's just non-convergent or divergent, right? And as a side note, for if you take just a um, 1 over x to the p power, and take the integral of that from 1 to infinity, and it doesn't have to be 1, right? It can be 2, 3. Um, I don't think 0 can work, but anything above like 0 for the lower limit, and then the upper limit is infinity, then it has a really interesting property. So if this p is more than 1, right, it could be 2, 3, 4. Integers are nice. Um, Fractions gets a little, at decimals gets a little wonky. But you will probably won't encounter them. So if p is more than 1, then it's convergent. This improper integral converges. Else, it'll be divergent. It will be like the value come out might be like infinity. And this uh, sort of relates to like the sequences that come later in this exam and the exam afterwards. But like this can be like, anything from like, let's say 2 infinity of like 2 over 2p squared, or 2 over 2, let's say p equal to something like 3, right? That p is more than 1, so this will converge actually. You can just cross out the 2. Let's make it 2 over 3. Right? It doesn't matter what the linear term is, as long as it's like a polynomial in the denominator, right? Because you can just pull this linear term in front. This is just 2 over 3, 1 over um, x cubed, right? And this part converges, and times a constant, that would still be convergent. All right, and then we can move on to the second example, where the limits of an integral are not infinity, but because there's a middle part that is somehow non-defined, that we need to use improper integral, where we take the limit of use a limit to replace the sort of undefined part, right? If you graph this out like I did above, you realize this is actually symmetrical. From -1 to 0 and 0 to 1, you can actually just take like 2 times one of these, um, and it should be the same. But for sake of doing this, we can do it's 0 to -1 to 0 and 0 to 1 for spreading this apart. So we have like an undefined in the middle, but we can say like it has 2 parts to this improper integral, and then we replace 1 with b from the negative side, right? Taking the limit from the negative, approaching 0 from the negative side, for the -1 to 0, right? It's this side, and then approaching 0 from the positive side, from the other one, right? From a to 1, and it's the same integration, and then same way of replacing the b and a for inside the equation, and then this time we have infinities, right? Infinity plus infinity minus 2 doesn't matter. That will result in an infinity, so therefore this is divergent. And the other thing for improper integrals is the comparison test. It's a easy way to know if a uh, improper integral is divergent or convergent. So the general concept is that you have a known series, a known integral that is convergent or divergent, like the the 1 over x to the p power example, right? It converges when p, because p is more than 1, and else it diverges, right? This is converge and diverge. Um, so this is a good starting point for your convergent test. And what I mean by that is that so if we know that this equation, right, 1 over x cubed, because that p-value is more than 1, we know that this improper integral converges. And we know that, and for like a equation like 1 over x cubed plus 1, right, since the denominator is bigger than the denominator over here, we know that for every value of the left side, that for the same x, the actual value of that equation is less than the right side, right? No matter what you have, because the denominator is bigger by 1, the value of the fraction is less. So for that reason, we can say that since this equation, this left hand side equation, is less than the right hand side equation for all values, and the right hand side converges, right? The right hand side, the 1 of x cubed, converges. That means that it's bounded by a value. That means that it equals a certain value. And since the left hand side is smaller than the right hand side, that has a value. Therefore, the left hand side also has a value, and it's also bounded by that value. And therefore, um, this left hand side equation will also converge. But the other ways to say it is the area, right? Because that's the definition of the integral, right? It's the area under the equation, right? Since there is a value for the right hand side, therefore, um, the left hand side would also have a value for that area that's not infinite. With the same idea, um, since we know that 1 over x diverges, right? So the right hand side diverges, and the left hand side is always bigger than the right hand side. Therefore, it will be like the area under that graph will be bigger than infinite, whatever infinite is, right? So therefore, that left hand side is also a has like an area of infinity. Therefore, the left hand side equation, the integral of the left side equation should diverge. So that's a comparison test, right? If you want to compare to something that converges, you can only draw a conclusion to the conversion, if the integral can converge, and you can only compare it to a uh, divergent integral if you want to see if this integral in question is divergent. Now moving on to sequences. Sequences are just a set of number that has like a relationship which you have to. So like for example, 1, 2, 3, 4, 5, 6. That's a sequence, right? That's the sequence of natural numbers. But we can write it in like different ways, right? We can write it, for example, we can write it in a formula which just says n, where a of n is just that's the name of the sequence. Let's just call it a of n. It's saying that from n equal to 1, the first number, I'm going to start saying it's just n, right? The first number is 1, the second number is 2, right? That's just um, well, the formula for the numbers in that set, right? For let's say like 2, 4, 6, 8, or it should be like the sequence would be keep going. That formula would be what? It would be like equal to 2n, right? The 2 times n is saying that at the first position, the number is 2, right? The position 1, which is n is the position, right? And then that's 2. The second position is 4, right? It's just 2 times the position. And the recursion relationship says that it's that the next number, which is n minus 1, is equal to the number at position n plus 2, right? Every time it's just plus 2, plus 2, plus 2. Moving on. We can conclude on the convergent or divergent of a sequence if the limit of that sequence infinity exists. So for example, you might have a sequence, we write it on the right hand side. Let's say it's like 2 over n. Let's say 2 over n. Then if I take the limit of 2 over n, right? This is like, this would be 0, right? Because it's 2 over infinity. At approaching infinity, then that would be like infinitely close to 0. And this is where the sequence goes like 2, 1, and then a half, right? It's dividing, or 2/3. It's going smaller and smaller. And that will eventually approach 0, and you see that this sequence converges as it converges on a number. The sequence converges on 0 for this sequence, but for other sequences, it might be 1, it might be 1/2. As you do more questions, do more practice, you see those. And the other example I ever bring up is sine and cosine, like the sinusoidal ones, where you have like a sine of like n pi, right? You're going from like the first number is 1, and this is -1, right? For if you can't really visualize what is this, I would recommend drawing a graph, right? This sine goes like here, 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 then go down again, right? It's going from 1 to -1, 1 to -1, oscillating. And this in sequences is divergent because it's never approaching a number. It's oscillating between numbers, and this is divergent by definition. And then we have series. Series is a sum of a sequence. Sum of this is where we use the big sigma summation notation, right? It starts from 1 in this case and goes to k, right? It's just saying that I'm summing from 1, 2, 3 all the way up to the number k. Then we have summation towards infinity. In this case, that's just a infinite series, right? This is 1/2 plus 1/4 plus 1/8 all the way to like 2 to the infinity power, which is really small. And this series will actually converge because every time you add something, it's just getting smaller and smaller and smaller, and eventually I think this approaches 1 if I'm not wrong. Another important topic is like partial sums. Nth partial sum is just saying the sum of the first n terms, right? For this series I have here, like the third partial sum would be the first 3 terms, right? And the fourth would be the first 4 terms, etc., etc. And then we're also interested in the convergent of series. Similar to sequences, if it has a sum, then uh, it converges, and else um, it diverges, right? If it has like a um, infinite sum, like the first series we have here, right? Because the k just grows bigger as you get to infinity, then it diverges, right? And then touching on again on sine and cosine, this similar to the sine this sine equation above, it goes like -1, then +1, -1, +1, right? And then the partial sums, right? The partial sums, the first partial sum is -1, and then 0, and it's -1, 0, and then oscillates. Once again, this does not approach a number, therefore it is divergent. Thank you for watching this video. The past exam archive and all the videos I did related to this exam will be linked in the description below. Please check them out if you're interested. Thank you.